So in this lecture, we're going to be talking about atoms and elements. Um, just some very formal definitions that you do need to know for your exam, right? Atoms, they come from the atomic theory of matter, and the thing that you really need to know about them is that they are the smallest individual unit of an element that retains the chemical properties or identity of that element. So that's a really important definition. Make sure you know that definition. And then, so what is an element then? An element, all elements actually are pure substances, uh, and are what things are built of. Everything is made of elements. They can't be broken down into any simpler substances. That's as far as it goes. Um, and then they're organized on the periodic table of the elements. So up here in the upper left-hand corner, we have some aluminum. I'll just put the atomic symbol there just to make it faster for me to do. But you can see that these elements are pure, right? They're homogeneous looking. Remember homogeneous from our last lecture? Um, the but that actually applies to mixtures, and these are not mixtures, right? They look homogeneous. They look like they're all pure elements. So down here we have sulfur, and then up here we have carbon. I'm not sure what's happening with that there. Let's try that again. There we go. So interestingly though, just if you didn't realize, and this has always confused me when I was a student, the symbol actually for gold is AU, and the symbol for silver is actually AG. Oh, can't see that. Let's write that again. AG. And the reason why I always got confused is because G is gold, G's and then you have the G down here for the silver, and then you have the U for. But it turns out that these are actually based on these symbols. These elemental symbols are based on the Latin word for the respective elements. So the Latin for gold is actually urium, that's why it's AU, and then the Latin for silver is actually argentum, which is interesting too. That's where the AG comes from. You don't have to remember that, but that's just something interesting. So let's go to the next page. Next slide. The periodic table of the elements is how we organize elements, and it was actually developed or compiled by Dmitry Mendeleev back in 1869. I think that the thing that's most important about this is that he was able at that time to categorize elements based on their atomic mass and also categorize them based on their properties. Like he arranged different elements into different categories based on similar properties. And in fact, he was able to actually leave gaps for future discovered elements too that were accurate in his periodic table. So that's a lot of foresight there. Today there are 118 elements that are organized that way. And I actually have over here a book, and in this book there's actually a copy of his original periodic table. If I can get it out real quick to show you. Right here. And if you see, that's the original one right there. Actually, let me maximize the screen for you so you can actually see it. Yeah, there we go. So this is his original periodic table, and can you read that? There we go. You can see how there's gaps right here, like right there, gaps right there, because those are places where other elements should go. But yeah, this is his original periodic table. Pretty interesting. So before we go forward, let me just go over a few interesting things about the periodic table on the surface, right? Before we dive too deep into it, these are called groups right here. Everything that's a column, right? So those are all groups. Elements are organized into groups based on the column that they're in, right? And then on the horizontal we have rows. These are all rows right here. and they're called period numbers. But even chemists will say this is row one, row two, row three, row four. And we'll see a lot of different periodic trends in these elements as far as their properties go. As you go down a row, or you go to the right with a column. But it's pretty interesting stuff. Um, Mostly, not mostly, but all the nonmetals are over here. My pencil's not working here. Nonmetals are over here, right? And then this little green stair-steppy thing right here. These are the metalloids. And just as a preview, metalloids are not metals, but they're like nonmetals that act like metals. That's why they're called metalloids. The suffix "loid" means in Greek, or it might have been Latin, I can't remember. It means alike something, but not actually it. And then everything here is all metals, right? And they subdivide these metals into even more smaller groups, but we'll talk about that later. Okay, next. So let's now take a look at some interesting elements, or I just forgot to write up here, interesting groups of elements. The first one I want us to look at here is group 1A or group 1, and group 1 is actually called the alkali metals. I spelled that wrong, like ala, but alkali, yeah, the alkali metals. And these contain like lithium, which is Li, sodium, which is Na. That's sodium's interesting because it's Na, but it's with an S, sodium. So actually, its Latin is actually natrium. That's why they call it Na. Potassium and so on. And if we take a look at these metals, over here, there's a picture of them like in these dishes here. The interesting about this is that these particular metals, which you wouldn't think they are, but lithium, sodium, potassium, and everything below them are actually very highly reactive in the water. So it doesn't look like there's anything in those dishes, but there's actually oil in those dishes. Oil, right? I'm sorry, I said water. They are highly reactive with water, but meaning the atmosphere, the water vapor and the air, and so they actually are stored in oil to keep them from being to keep them from reacting with the water in the air, the water vapor in the air, lithium, sodium, potassium, and all the ones below it too. So another interesting group here is group 17 or 7A. These are the halogens. We'll talk about the halogens a lot later on, but they're all gases. So chlorine gas, for example, which was used a lot in, for example, World War I as a weapon, is a kind of a greenish, yellowish gas. We have bromine gas here, reddish, and then iodine gas, which for some reason that's misspelled right there. There we go, iodine gas, which is kind of like a purplish blue color. Notice too that we'll talk about this later, but lithium, solid lithium element is just Li, but chlorine gas and bromine gas and chlorine and iodine gas are all have a 2 after their symbols. There's a specific reason for that, and we'll talk about that later. So since this is like an allied health emphasis class, I'm obligated to talk about how certain elements are essential to life. So let's talk about some life elements. Let me clear some stuff out of the way here. So elements that are marked in red, for example, hydrogen and carbon, nitrogen, and oxygen are known as the are major elements that are present in the body. Blue, they're macro minerals, so they're in higher amounts but lower than the major elements. And then there's the micro minerals, which we have trace amounts of each of those. So just to go through this, kind of quickly, but not really not anything you really need to know for a test or anything like that. But it's interesting to know things like oxygen and carbon and water and nitrogen, right? Obviously, oxygen, carbon, And hydrogen and nitrogen are very important, not just because hydrogen and oxygen are in water, but carbon and nitrogen, along with those other three, make up things like your biomolecules, like DNA and your proteins. Hydrogen, especially, also is important because you'll see that hydrogen is acidic, not hydrogen itself, but a proton, a hydrogen proton is acidic, and so it helps you regulate your pH and it's your stomach acid and stuff like that. So those are your major elements. Macro minerals are like calcium, phosphorus, potassium, chlorine, sulfur, um, and uh, sulfur and magnesium. And so, why are those guys important? Of course, calcium is in your bones. Phosphorus is, I didn't know this, but phosphorus is actually in your teeth and your bones. But more specifically, though, phosphorus is in DNA. It's also in like your energy metabolism too, because when you talk about things like ATP, adenosine triphosphate, so phosphorus is in that. Um, Potassium is in your cells. You use it for muscle contractions and nerve impulses. Chlorine is actually the fluid outside and inside your cells. That's why, for example, in your blood, you have to have like a saline solution, your serum. And so saline solution is basically sodium chloride or salt, right? And that chloride is that chlorine that we're talking about. And it helps regulate the fluid inside your cell, whether it's like super concentrated or super dilute, and we'll talk about that later. Sulfur is actually very important in proteins, um, and in the liver, in insulin, and vitamin B1. And then sodium, I already mentioned, is a part of sodium chloride, for example, and that's in your plasma, serum. And so it helps regulates the fluid outside the cell, and fluids inside the cell, the water balance, as it were. And it also helps with muscle contractions, involved in muscle contractions and nerve impulses. And then a lot of people don't realize this, but magnesium is actually very important in ATP. Because when you're talking about ATP, adenosine triphosphate, we'll look at this a lot later on in the semester, but it has three phosphate groups, which we'll talk about what phosphate groups are in a minute. Um, Not in a minute, but in a little bit. But phosphate groups are basically as phosphorus with four oxygens around it, and then connected to something else, which we'll talk about later. But those oxygens are really electronegative, so they really like electrons, um, and they are really close to each other, so they kind of like repel each other. And so magnesium actually acts as a stabilizer for the phosphate uh, before it's used for any energy or making DNA or anything like that. So magnesium is very important. Now we get to the trace minerals. The trace minerals are the micro minerals. We have iron, which we talked about before, in hemoglobin, and it's what actually binds to the oxygen that your hemoglobin takes around to the cells in your body. Silicone is important for growth and maintains the growth and maintaining the bones and teeth, your tendons, your ligaments, your hair, your skin. Um, Zinc is important in metabolism, and it's important in DNA synthesis, your immune system. Copper, also needed in your blood vessels, and regularly helps with your blood pressure and your immune system. And then manganese, which is instrumental in blood clotting and metabolism and bone growth. So obviously all these elements are very interesting. You don't, like I said, you don't have to actually remember all that for a test or anything like that, but it's just interesting to know. There's actually a chart in our book that you can look at to see all that stuff. Since you guys can actually access your book now, let me know if you still can't access your book. Okay, so as we talk about atoms, we need to talk about um, Dalton's atomic theory. Again, this is, whenever I have actual words up on the screen, it means it's something that's important that you might be asked about, and so you need to know these words very specifically, or these definitions, or these theories. So Dalton's atomic theory states that all matter is made up of tiny particles, right, and called atoms. And then all atoms of a given element are identical to one another and are different from atoms of another element, right? I mean, that's pretty obvious, but it is stated in theory. Atoms of two or more different elements can combine to form compounds, which we'll talk about a lot later in the lecture. a particular compound is always made up of the same kinds of atoms and the same number of each kinds of atoms, and you'll see that when we talk about compounds later. Then a chemical reaction involves the rearrangement or separation or combination of atoms. Atoms are never created or destroyed in a chemical reaction. So that's one of the laws of thermodynamics too, by the way. Matter cannot be created or destroyed. So we'll talk about that later. Again, I just wanted to reiterate that the atom is the smallest particle of an element that retains its chemical properties of that the chemical properties of that element. Right. So just remember that. That's an important. I've said it on 2 slides on because it's important. We saw aluminum earlier. So there's some aluminum foil, and this is what the atoms in aluminum look like. They're actually arranged. It's very organized in the aluminum foil. That's what makes aluminum foil a solid, right? Because remember from the last lecture, solids solids have their atoms very tightly packed, right? And then this is very interesting. This here is a real picture of gold atoms, right? AU. See, I remember not AG but AU. Atoms of gold, right? And this was taken on a scanning microscope, and the scanning microscope magnified the atoms of gold to 16 million times. So that's how much you have to magnify a piece of gold to see the atoms. So let's talk about the structure of atoms now. So really this slide should be entitled "The Structure of Atoms." So let me just write that up here. Structure of atoms. So back in the day, this guy named J.J. Thomas, he did this experiment with a cathode ray tube. And when he did this experiment with the cathode ray tube, he figured out that if you don't know what a cathode ray tube is, it's literally a tube that has gas inside, some kind of gas, just air. Air would work too. And he put an electrode on either side of this tube, and so that's a cathode tube. And he ran electricity through it, and he noticed that the particles inside of this tube, air molecules inside this tube, were charged when he did that, because he was able to conduct electricity using the ray tube, using the cathode tube. And so he surmised then that that atoms must be composed of charged particles, like an electron, which is negatively charged, and then in some kind of a medium that's positively charged. So this became known as the plum pudding model. And so in the plum pudding model, the negative electrons were the plums, and then the medium that was positive that those electrons sat in was called the pudding, the positive pudding right there, right? So later on, though, he and a guy named Ernest Rutherford, they collaborated so that Rutherford could try to do an experiment using the scientific method, like we talked about in the last lecture, to see if Thomas was correct. And so they came up with this experiment right here, and this is called Rutherford's gold foil experiment. Rutherford's gold gold. There we go. Foil experiment. Right, and in this case, or in this experiment rather, he had positive particles right here, and he let these positive particles, shot them at a piece of gold foil, which is there, and then around that piece of gold foil had had a fluorescent screen that was able to detect things that were happening around the gold foil. So when he shot those positive particles into the gold foil, he noticed that the positive particles are actually being deflected, like it would shoot in, right, and be deflected by things in a very specific ways, right. Some of it would pass through, but not all of it would pass through. Some of them got deflected, obviously. So, and since they were very specific in where they were being deflected, This experiment is what this experiment is what leads us to our modern understanding of what a atom is composed of. Right, atoms are composed of protons, which are in the nucleus, neutrons, also in the nucleus, and then surrounded by electrons. So it turns out that JJ was actually wrong. JJ Thomas was wrong about his plum pudding model. So it was a pretty cool experiment to do, and obviously his hypothesis, Thomas's hypothesis, was declined. So, but they came up with an explanation, which is good. So let me clear off some stuff here so we can see what's going on. So if you again we take a look at the lithium metal right here, the lithium that's actually sitting in some oil so it doesn't explode on you when it reacts with the water vapor in the atmosphere. We can take a look closer and we see that there are lithium ions in there. But if we look even closer than that, we can see that in the nucleus of in the center of the lithium ion is a nucleus that's positively charged, and then on the outside are surrounding that nucleus are electrons that are negatively charged. We took a closer look at that nucleus right here, and we can see that the nucleus is actually composed of neutrons and protons, which we'll talk about in more detail later. But that's why it has an overall positive charge, because neutrons have no charge, while protons have a positive charge, right? And then this is also very interesting too. The diameter of a nucleus, lithium nucleus, is approximately 10 to the minus 15 meters. So that's 15 zeros after a decimal point. Meters. That's really, 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 really small. Super small. Okay. Anyway, so looking at each particle that we're just each subatomic, we call this a subatomic particle because we're going below the atomic realm, right? Protons have the symbol P or P plus because they're positively charged, and you already know that they have a +1 charge right here, and they have a mass of about 1 AMU, or specifically 1.007 AMU, and they're located in the nucleus. Neutrons, they have 0 charge, so their symbol is N naught or N0 superscript. 0 charge, of course, almost the same weight as a proton. The more interesting thing is that, not that the symbol of electrons is E with a negative superscript, or that they're -1 charge, you already knew that, but the fact that they are very, very light. They're 0.00055 AMUs. Oh, by the way, if you didn't know what an AMU is, an AMU is an atomic mass unit. And we'll talk about it later. Atomic mass. Mass unit. There we go. Atomic mass unit. Moving forward, we're going to go through this pretty fast here. Let's talk about the different parts of the periodic table that represent atoms. So the first thing is that when we're using lithium again as the example, the atomic number here, that's equal to the number of protons we have, right? That's equal to the number of protons we have. So for lithium, since its atomic number is 3, right, that means lithium has 3 protons. Same thing with carbon. Carbon has an atomic number of 6, right, which means it has 6 protons. So the important thing to know about that is the number of protons in an atom is what identifies that atom's atomic number and that atom itself, right? And that element itself. So just remember that. So the number of protons plus the number of neutrons, right, equals its mass number. And we'll talk about that in more detail later, because you can have an element or an atom that has the atomic number for the number of protons for a certain element or a certain atom, but then have a different number of neutrons, and those are called isotopes. We'll talk about that later. Mass numbers are very important when you're talking about isotopes. But just for this particular slide, remember that the number of protons plus the number of neutrons equals the mass number. And then, since that, since you'll be able to, since you know that, you can then use the mass number minus the atomic number to get the number of neutrons that are in the atom, right? To get the number of neutrons in the atom. And this little note here that says the mass numbers apply to only specific atoms of an element, and that's what I mean when I say those mass numbers are different for different isotopes, which is atoms that have the same number of protons but different numbers of neutrons, and we'll talk about that a little bit later. And then, I guess one more important note to say is that neutral atoms are neutral, so they're neutral, and they're neutral because the number of protons equals the number of electrons, right? Again, that doesn't affect the mass number because the number of electrons isn't in the mass number calculation. So that's why atoms are neutral, right? Atoms are neutral because the number of protons equals the number of electrons. And we'll dive deeper into that in a second too. Oh, look, the next slide is about isotopes. It's just talking about that. So we'll start out by talking about lithium again. No, that's actually magnesium. So magnesium is actually in the second group of metals, right here. Not in the first group, like lithium is. And these are called the alkali earth metals. Alkali? No. Let me write that again. Alkali earth metals, right? They're the alkali earth metals. And this is interesting, right? Because you notice that since it's in the second group here, everything that was in the first group, like the lithium, the lithium, the sodium, everything on down, had to be stored in oil because they're highly reactive with, and you'll figure that out why later, but they're highly reactive with the water vapor in the air, right? But magnesium, though, since it's in the second group, the alkali earth metals, right? They're actually stable in air. They're not highly reactive with the water vapor, so you can store them just as is. This is just a little spindle of magnesium metal just sitting out there, right? So that's an interesting thing because remember I said that when Mendeleev categorized the periodic table, he put atoms of like properties into the same groups, right? And so when he categorized lithium and sodium and all those guys in the group one, it's because they were super reactive with the water vapor in the air. And then he categorized the alkali earth metals, which is magnesium and those guys below magnesium, because they were not, right? And there's some more detail there. It's more complicated than that, but that's basically what's going on there when you try to group atoms of like characteristics or properties together. Back to the topic at hand in this slide, though, isotopes. Notice we look at these atoms of magnesium here, right? And magnesium can actually, its atomic number is 12, right? And so, but it can actually form isotopes, 3 here, right? It can form isotopes. So if you look at, the special notation that they have here, normally isotopes are written in this notation, okay? And so what that means is, I'll just draw it up here, right? We'll just use anything as an example here. For example, we'll use, I guess I can use magnesium again since it's the example here. If you have magnesium, there's a number that's in the upper left-hand corner. Sorry, I'm trying to find space. And then there's one in the upper left-hand corner. There's one in the bottom left-hand corner. Upper left-hand corner and upper left-hand. Sorry, one more time. Upper left-hand corner and the bottom left-hand corner, right? And so when we're talking about isotopes, this number here in the upper left-hand corner is the mass number that we were talking about. Let me try that again. Oh, I see what's happening here. I lost connection to the thing. here we go. I'm back. The mass number, right? The mass number that we were talking about from the last slide, and then this bottom left-hand one is the atomic number from the last slide. So that means then this is what? This is also the number of protons. Oh, losing connection again. Protons. Number of protons, right? That's the number of protons. So this first isotope of magnesium down here, you can see that it has 24 up there in the upper left-hand corner and a 12 in the bottom left-hand corner, which means that this magnesium has a mass number of 24. And it has a number of protons, or an atomic number of 12, which means its number of electrons is also 12, right? So this particular first isotope of magnesium is actually the most common isotope of magnesium. You can see down here that of the 100% of all magnesium atoms, 78.7% of it is magnesium 12. Sorry, magnesium 24. All right. So let's look at the second one. The second one says, the second one right here says 25, so that's its mass number, minus 12 for its number of protons, right, equals 13. Whoops. 13, right, equals 13, which means that's the number of protons it has. Sorry, number of electrons. Sorry, again, number of neutrons. 13 neutrons, right? That's 13 neutrons. So that's an isotope of magnesium. And of all the magnesium atoms in the present, 10% or so is magnesium 25 with 13 neutrons, as compared to magnesium 24, which has 12, right? And then the last isotope of magnesium is magnesium 26. 26 minus 12 equals 14 neutrons. And magnesium 26 then has, again, 12 protons and 14 neutrons. And it has an abundance, we'll call that abundance, by the way, an abundance of 11.17% of all magnesium atoms are magnesium 26, right? So when you look at then, the question then is then, you know, everybody knows that this is called the atomic mass right here on the periodic table, that number with the decimal point, that says 24.31. Where do we get that number from? Well, that number is actually an average of all the masses of all the isotopes of magnesium. So that's true of any element on the periodic table of elements. The atomic mass is actually the average of all the atomic masses of all the isotopes. Not to be confused with the mass number. The mass number is what you use to figure out how many neutrons you have. The atomic mass is the average of all the masses of the isotopes of a particular element, and in this case, it's magnesium. Right. So let's look at some other isotopes. Let me clear this screen real quick, and we'll look at some other isotopes. One of my favorites actually is chlorine. And the reason why chlorine is one of my favorites is because we have chlorine 35, right? And we also have chlorine 37. The most naturally occurring chlorine is chlorine 35, and its isotope is chlorine 37. I don't think we need to go through and do the easy math to figure out how many neutrons each one of those isotopes has. Right? It's just simple minusing, right? But the interesting real-world application to this is in forensics. We use a lot of mass spectrometry, right? We find a piece of trace evidence which is like some kind of material that we don't know what it is. It's a parent something, a parent piece of plaster or a parent fiber or something like that, or anything like that, or even drugs. And so to try to identify, and if you didn't know that, by the way, forensic science is all about identification. That's why back in the day, before there was like CSI and before there was Bones and all those other forensic science shows, all the units for doing forensic science were actually called ID or identification. Because really, what are you doing as a forensic scientist? You are trying to identify something, right? Um, Whether it be a suspect or a piece of clothing or blood or a bullet or whatever it is, you're trying to identify something. So when we have trace materials and we want to identify what it is, we'll stick it into the mass spec to see what its mass the mass spectrum to see what its mass spectrum is, and then the mass spectrum, uh, which is just a whole bunch of peaks that are very specific to a particular molecule, right? Can be uh, run against a library of molecules, and you can match them up to a library. So what does that mean? Why does that have to do anything to do with chlorine? Well, oftentimes though we can have pieces, or not pieces, but we can have a trace that isn't in the library and we don't know what it is, and we have to kind of try to identify the molecule without having the benefit of a library. And one of the things that you see in a mass spectrum, for example, is something that looks like this, right? A bunch of peaks like that, right? Well, for chlorine, since it has two isotopes, one at 35 and one at 37, chlorine 35 and 37, notice that chlorine 37 is actually about a third of the abundance of chlorine 35, right? And so whenever we see a peak, or two peaks rather, that are right next to each other, right, where one peak is approximately 37 mass units, or weight of mass of 37, and one right next to it is a mass of 35, and their abundance, right, is approximately one third of each other, we can immediately assume then that this must be a chlorine in the molecule. I mean, the rest of the molecule still needs to be figured out, but that's like one of the first steps. Like you see 2/3 peaks at 35 and 37, and you know that there's a chlorine present in the molecule, which is pretty cool. Um, that's an oversimplification of the entire process, but I just wanted you to know that we do that in mass spectrometry. Um, so there's some other, interesting, not interesting, but yeah, they're all interesting. Some other isotopes that are of lithium. So lithium has lithium 6 and 7 here. Carbon, of course, has carbon 12, 13, and 14. We actually use a lot of carbon 13 here for NMR, which is nuclear magnetic resonance. Trying to decipher a molecule's structure from using magnetic resonance, nuclear magnetic resonance. Then carbon 14, that's actually a lot for, we use that to do carbon dating, right? Carbon dating. Right? There's also the most common, so also we have oxygen here. The most common oxygen is oxygen 16, but there's also oxygen 17 and 18. There are more fluorine. I don't know what happened to the rest of the fluorine isotopes, but that's okay. Maybe I just forgot to type them in there. Sulfur has 4 different naturally occurring isotopes. Potassium has 3 naturally occurring isotopes, and copper has 2 naturally occurring isotopes. And that's just examples of different things. That's just examples of different isotopes. There are more. The periodic table is littered with different isotopes of different atoms. Just one takeaway message from this particular slide. Just remember that that isotopes are atoms of the same element with different mass numbers. And what does that mean? That means that they have a different number of neutrons, even though their number of protons is the same. So that is the takeaway message from this slide. So now we go from talking about protons and neutrons and isotopes to talking about electromagnetic radiation, which you may be asking yourself, what's the connection between that and atoms? Well, electromagnetic radiation has everything to do with electrons. So, radiation has a very negative connotation to it because one might think that being exposed to any kind of radiation will cause you to be sick, like cancer or something like that. And it's true that a lot of the, a lot of or some of the electromagnetic spectrum can cause that. For example, gamma rays or X-rays cause some damage to your body and your cells. Uh, you need to realize that um, electromagnetic radiation actually encompasses the entire electromagnetic spectrum, and that begins with um, that goes all the way from radio waves all the way to gamma rays, right? So let's first talk about the part of the electromagnetic spectrum that you are most familiar with, which is the visible spectrum. The visible spectrum actually begins here at 700 nanometers and ends at 400 nanometers right there. Um, and it's what it looks like. It's the colors of the rainbow, right? That's the visible spectrum, the colors that you see. If you remember back in the first lecture, I was talking about how I had a professor who would ask us what our favorite color was, and he expected us to respond with some kind of numbers. Well, what he was asking us to respond with was actually the nanometers, or the wavelength of our favorite color, right? And so when he said his favorite color, he said his favorite color was actually 663 nanometers, right? That's actually right about there. And you can see how that corresponds to red, right? Over here on the other side, if someone asked me what my favorite color was, I would say 475 nanometers, which that's right about there, which corresponds to blue. That makes sense, right? So every color that you see corresponds to a certain energy of a certain amount of energy in EM, in electromagnetic radiation, right? And as the wavelength actually decreases, right? So here you have 700, and over here you have 400. As the wavelength decreases, the energy gets higher. So there is more energy in blue light than there is in red light, right? And if you expand that to the rest of the electromagnetic spectrum, you can see how certain types of electromagnetic energy electromagnetic radiation can be damaging, and others are just benign, right? So, interestingly, if you take a look at here, the electromagnetic spectrum, the part of the electromagnetic spectrum that's visible that you can see is actually right here, this very small part right here, right? Very tiny part of the entire electromagnetic spectrum. So let's move towards higher energy from where we are most familiar. The next type of electromagnetic radiation after visible is called ultraviolet. Okay, ultraviolet is pretty high energy. It's got 10 to the minus 8 nanometers, which is pretty high energy. So it turns out that when you do some calculations to figure out what kind of energy is involved in UV or ultraviolet light, it corresponds to the kind of energy that's required in the breaking of bonds. The breaking of bonds, right? Um, so that's just about somewhere around 113 kilojoules per mole. So if you ever wondered why getting too much sun gives you skin cancer, it's because this 113 kilojoules per mole right here, this 113 kilojoules per mole is the approximate energy of a carbon-carbon single bond, right? A carbon-carbon bond. And it turns out that a lot of your DNA is made up of carbon-carbon bonds. And so when you get exposed to UV light, that energy, about 113 kilojoules per mole of energy, is able to break this bond and rearrange the atoms in your DNA into something else, and that's why you get skin cancer. So think about it like this: ultraviolet light corresponds to the energy of bonds and breaking bonds, right? That's about the same kind of energy. Also, by the way, It's called ultraviolet because the very last color here is violet, right? And then ultra is Greek for above, right? So ultraviolet means above violet. That's how you remember that ultraviolet comes after violet. Um, if we move even further, we get to X-rays. X-rays are pretty dangerous too. They're around 10 to the negative 9 to 10 to the negative 10 nanometers. Ooh, that's super small. And you wonder why someone has to wear like a lead vest to take your X-ray, and that's the reason why, right? I mean, you're not just like messing up your DNA, but you're messing up your proteins at that point too, right? X-rays are pretty damaging if you're consistently being bombarded with X-rays. And the strongest of the electromagnetic radiation is called gamma rays. It's 10 to the negative 11 right here, right? That's really, really small. So it's got lots of energy. Um, it's so strong that gamma rays can actually make the Hulk, if you recall. The Hulk, Bruce Banner, was exposed to gamma rays, and it not only changed his DNA, it also changed his proteins, like, in real time, so that he can become the Hulk when he gets upset, which is kind of crazy, right? So just remember those as you get further and further to smaller energies in wavelengths. It's the stronger it is. So let's go backwards now. Just below um, the visible spectrum right here is infrared. By the way, the last color, right, of the visible spectrum here is red, and infra is Greek for below, and that's why they call it infrared. Infrared's a pretty wide wavelength, so it's pretty weak, but most of the heat you feel is actually infrared, right? Most of the heat that you feel is infrared radiation. The interesting thing about that is that the energy of infrared right here corresponds to about 4.8 kilojoules per mole. And it turns out that that's not strong enough to actually break a bond, but what it can do is it can actually stretch bonds. It can stretch a carbon-carbon bond. It can actually stretch bonds. Excuse me. So when we get later on into our organic chemistry section of the semester, we'll talk about IR spectroscopy, where we use the frequency of stretching in bonds to identify what kind of functional groups there are, or groups of molecules that are there. Right below that, infrared is microwave. Microwave is pretty small. You're all very familiar with microwaves because you have a microwave oven probably somewhere available to you. You have cell phones. Microwaves are actually well tuned to vibrate and flip the dipole moment of water. If I can spell dipole right. And what that does is that it makes it very convenient because you can use a microwave to heat up your food if it has water in it. So you ever notice why? You ever notice that you can't? It's not easy to heat up food that's dry, that's super dry. But if it's got water on it, or if you put like a paper towel with water on top of it, it heats up the food really fast in the microwave, and that's because microwaves work on the dipole moment of water. So those microwaves are perfect, the perfect amount of energy to vibrate water molecules. In simpler terms, we'll talk about that later, maybe, but that's what microwaves correspond to. And then, if we go even further down, we have radio waves, and in radio waves, that energy is super small, very big wavelength, right? Because we're at like 10 to the 3 now. Right, that's 10 to the 3 now, right, for radio waves. It's a pretty big wavelength. So we use, you know radio waves because you listen to the radio, if you still do listen to the radio in your car when you're driving to work or whatever like that. And And so I'm originally from Houston, and we have a radio station called 104 KRB, and it's like 104 megahertz, but that radio station is transmitting at this wavelength right here. And so the uh, the interesting thing when it comes to chemistry, though, that is that not only can a radio wave transmit sound, right? It actually is the perfect frequency to excite a proton and move it up to a higher energy level, and then relax it, right? And that's the basis of using NMR, which is nuclear magnetic resonance, to elucidate the structure of molecules. But more commonly, it's the basis for using MRI, which is magnetic resonance imaging. That's using radio waves. So that's pretty interesting stuff. So the takeaway from this then is that even though we were talking about protons down here with the radio waves, really we're concerned with electrons, and electrons they can be promoted or excited to a higher energy level, right? And so if you look at this, for example, right here, this picture right here, we have an electron at the ground state, and it can get excited, and when it gets excited, it moves up to an excited state, right? This energy level right here, this little gap here, is quantized. And you might ask yourself, what the heck does quantize mean? Quantized just means that every electron has a very specific energy gap between its ground state and its excited state. And it's only when it absorbs the exact right amount of energy that it can be promoted to that excited state energy. So what that means then is that electrons just don't have random energy levels all over the place. They all have specific energy levels that are quantized based on their position in an atom or their environment or whatever, right? In a molecule, they have very specific specific energy gap between its ground state and its excited state. So that is what quantized means. That's what quantized means. So once an electron is promoted, it can actually be relaxed and come right back down again to its ground state. And when it does that, it actually emits energy when it does that, because the energy has to go somewhere. And remember, energy cannot be created or destroyed, or matter for that matter. And both of these examples show that right here. Energy is being released as an electron is relaxing from its excited state. And excuse me, in the case of visible light, for example, the colors of the rainbow, right, or the colors you just see all over the place, what's happening there is the light from your light bulb or the light from the sun or wherever is hitting the molecule, right, of dye or ink or whatever, right, and the electrons from that molecule are being promoted, right. And when those electrons get promoted, get excited or promoted to that higher energy level, they have to relax. And when they relax back down to the ground state, they release energy, and that energy is in the form of a color, right? And then you ask yourself, well, how do you know what color it is? Well, the color is dictated by the electron's energy gap that I was just talking about between the ground state and the excited state. So if you're talking about, for example, you have a blue shirt, and you're wondering why that shirt is blue, it's because that dye that they used to color the shirt with has a molecule in it that has electrons that have an energy gap between its ground state and its excited state that is somewhere in the blue range, right? The blue visible spectrum, here near the 475 or the 400 area where my favorite color is, and that's how you get blue, and that's true of all colors. You can actually use the electromagnetic spectrum and the visible wavelengths to identify certain atoms and certain elements. And one of the ways you do that is down here I have a flame of barium, right? Uh, Barium is an element, and when you uh, uh, when you have a burning flame with barium in it, it actually emits green light, right? But when that green light is split up with a prism, it splits into its constituent colors, and you can see this is the light spectrum of barium, right? So it's the light spectrum of barium. So um, these energy levels that we're talking about with the that the electrons get promoted to higher energy level excited states and such, right? They are quantized, like I said before, and they are represented by what we call the principal quantum number. The principal quantum number. And it's literally, it goes from 1 uh, to 7, right? So 1, 2, 3, 4, 5, 6, 7. And each energy level is, you have 1 is the bottom, and then 2 is the next one, 3 is the next one, and the higher you go, all the way up to 7, it's the highest energy of the quantized energy levels. Um, so the other thing to know too is that let me clear some space here real quick. The other thing to know too is that it's only electrons that are in the outer shell of an atom, outer electron shell of atom, that can be excited to a higher energy level or promoted to a higher energy level when it absorbs energy. And what I mean by outer shell is that if I have an atom, for example, of neon, the first electron shell can only hold 2 electrons, right? But if you look at the periodic table, neon actually has 10 electrons because its um, atomic number is 10, right? Which means it has 10 protons, and for it to be balanced, it has to have 10 electrons. And I've already put 2 in the first energy shell, so the next 8 have to go into this outer shell, and they usually pair up like this. And there's always 8 in that energy shell. This is actually called the valence electron shell, right? And those electrons are called valence electrons. So generally, um, only valence electrons can be promoted to a higher energy level or absorb energy so that they can go up to a higher energy level. So yeah, just remember, this is the inner shell, has 2 electrons, and this is the outer shell. It has 8 electrons for neon, less or more depending on the element you're using, right? As an example here, and so those electrons in the outer shell are called valence, right? So let's then put them into their energy levels. The inner shell then is what we call n equals 1, and there are 2 electrons in the lowest shell, right? Well, the next one then would be called n equals 2, and there are 8 electrons in that shell, and that's how you would say that. If there were more, then we'd go up to, because we're going only 8 at a time, it's the octet rule, which we'll talk about later. There would be more, like n equals 3, if it was a different atom that had, or element that had more electrons. So, moving on. Let's talk about some periodic trends. Like I was telling you before, we had the we had the alkali earth metals, which all are very reactive to the water vapor. Sorry, not the alkali earth metals, the alkali metals of group 1. We had the alkali metals of group 1, and they're all very reactive with the water vapor in the air, and so you had to store them in water. No, that's bad. We had the alkali metals that were in group 1, and you had to store them in oil because they're super reactive with the water vapor and the air. Um, and then we had the alkali earth metals, which were in group 2, and they're not as reactive, so they didn't have to be stored in oil. Uh, but those kinds of trends are all over the periodic table, so let's talk about those very briefly. Um, we were just talking about this in the previous slide, right? We were talking about valence electrons. Um, and so as you go across the periodic table, so this is hydrogen over here, and this is helium over here, which is on the other side of the periodic table, right? As you go across the periodic table from the left to the right, the number of valence electrons increases, right? Um, so you can see, let's use lithium because lithium is in a row with a lot of other ones. Lithium has 1 valence electron, as you can see there. Beryllium has 2 electrons, valence electrons. Boron has 3 valence electrons. Carbon has 4. Nitrogen has 5. Oxygen has 6. Fluorine has 7. And we already talked about neon, which has 8, which is the full octet. And we'll talk about more later, right? In case you didn't already know, group 8 here is known as the noble gases. And they're known as noble gases because they have full electron outer shells or valence electrons at 8. And so it's been generally known or generally studied that they're not very reactive with things. And they don't need to be because it's having less than 8 or a full outer shell like these other ones here, fluorine, oxygen, nitrogen, and then the metals like lithium, beryllium. It's having less than a full octet or full outer shell is what makes things want to react with things, right? So that they can get a full shell of electrons, which we'll talk about a lot later, right? So as we as we go down the periodic table, for example, with lithium, sodium, and potassium, which is group 1, the distance between the nucleus and the valence electron shell, or the outer electron shell, increases. Right? That's pretty obvious there. That translates to also meaning that not only does that distance, you can also even call it like a diameter, as that distance increases, that means that as you go down a column on the periodic table, atomic size gets larger, right? The size of the atom itself gets larger because the electron shells are further apart, and there are more of them too. And then as you move to the right of the periodic table, as you move to the right of the periodic table, the atom size also increases. Right, the atom size also increases. And then the next periodic trend to talk about is the ionization energy. As you go to the right of the periodic table, the ionization energy increases. And as you go down the periodic table, the ionization energy decreases, right? So what does that mean? Well, what is ionization energy? Well, ionization energy is the energy that is required to basically rip an electron from an atom, right? And so, as you can see, as you go further and further down the periodic table, the ionization energy decreases because you don't need as much energy required to rip off an electron from, for example, potassium, as you would, for example, lithium or sodium, right? Which makes them more reactive. Which, as you go down, it makes them more reactive. And then, last but not least, metallic character obviously increases as you go down the periodic table, but it decreases as you go towards the right of the periodic table because as you approach the right of the periodic table, you have your nonmetals over here. Right, you have your nonmetals. So that's pretty obvious too. So the last couple of slides are about radioactivity, and we already talked about in a previous slide about isotopes, elements of the same atomic number, meaning the same number of protons, but having a different number of neutrons. Well, some of those isotopes can be radioactive. What does that mean to be radioactive? What it means is that the nuclei of that isotope is so unstable that in an effort to become more stable, it will emit little particles of energy. And those particles can sometimes be dangerous. So if we take a look at the type of particles that can be emitted by these radioactive isotopes, the first type of particle is called an alpha particle, right here, right? And the interesting thing about an alpha particle is that it is the same thing. It looks exactly like a helium nucleus, a helium nucleus. So it's kind of small there, so I can't really draw there, so I'll write it out here. If you remember when we're talking about isotopes, we always write the elemental symbol, and then the number in the upper left hand is the mass number, and this mass number is 4, right? And then the bottom number is the atomic number, which is the number of protons, 2, right? So that means that this is got 2 protons, and 2 minus 4 makes it 2 neutrons, right? Which is exactly the same as a helium nucleus, right? So an alpha particle, like I was saying, right, is a helium nucleus, and it has a charge of +2. Charge of +2, right? So as we go down, let me just clear off here so we can see the small little chart I have. The next particle is called a beta particle. And beta particles, you can see its symbol has an E right there, right? It has a little E. Well, that's because these are just high energy electrons. High, let me write that again. High energy electrons. By the way, if you don't remember, when I write a big E like that, it just means energy. So those are high energy electrons, right? The next type of particle is called a positron. Right there, positron. And what is a positron? It's literally the same mass as an electron, but it has a positive charge. So basically it's an electron with a positive charge. Kind of weird, right? But that's what a positron is. And then last of the things that we haven't covered yet is the gamma ray. And a gamma ray is pure energy. And like we were talking before, in the electromagnetic spectrum, you don't want to be exposed to gamma rays. That will definitely mutate some DNA, some proteins, and be a bad situation, right? So the next picture down here is just kind of like, let me clear off the screen a little bit. I don't really think I need to go over what a proton or a neutron is, because those nuclei can also expel protons and neutrons too, right? But you already know what that is. So the next picture is just kind of a summary of the chart that we just did, kind of in pictorial form here, right? If you have an alpha emitter, a radioactive isotope that actually emits alpha particles, this alpha emitter will lose a helium nucleus, right, and become a new element. And in that process, it will lose 4 from its mass, and its atomic number will go down by 2, because it lost all that when it emitted that helium nucleus. If you have an isotope that's emitting beta particles, recall that beta particles are just high energy electrons, right? They're high energy electrons. When it loses that high energy electron, when it emits it, right, it becomes a new element. Its atomic mass stays the same, right? Its atomic mass stays the same because it's basically the weight of an electron. But its atomic number goes up by 1. Its atomic number goes up by 1. And then if you're a positron emitter, if it's a radioactive isotope that is emitting a positron, you'll lose a positron, of course, which is basically a positively charged electron, the same weight as an electron but positively charged, right? You come up with the same you come up with a new element, right? But you still have the same weight, same mass number rather. I'm sorry, same mass number. But this time, instead of gaining an atomic number, you lose one. You lose one. And then if you're a gamma emitter, right? Remember that a gamma emitter, which is this gamma 00 here, is pure energy. And when you emit that, you're emitting all that unstable energy to become a more stable nucleus of the same element, which means that your mass stays the same, your mass number stays the same, and your atomic number stays the same. You don't change to become a new element when you're a gamma emitter. So that's the biggest thing to remember there. Gamma emitters are the only ones that stay the same after they've emitted their gamma radiation. The other three that emit alpha, beta, or positrons will become a new element, losing stuff in the process. So this other chart over here is just displaying the distance that different particles can travel. So an alpha particle, like through the air, can go 2 to 4 centimeters, which is not very far. A beta particle can go about 200 to 300 centimeters, which is pretty far, but not that far. But notice that a gamma ray can travel 500 meters. So that's why you got to be super careful around gamma emitters. Usually these are, like I said, radioactive isotopes of elements. Through tissue, though, an alpha particle can barely go through your tissue. It goes like 0.05 millimeters. Same with the beta particle, right? But again, a gamma ray can penetrate your tissues by 50 centimeters or more. That's why you get the Hulk when you're exposed to gamma radiation. Shielding, like paper or clothing, is sufficient to block an alpha particle. Heavy clothing, even lab coats, are enough to block block a beta particle. But you need a lead vest or thick concrete, but you'd much better to wear a lead vest to block a gamma ray. And like I was saying before, these are usually radioactive isotopes, and I've already mentioned some before, but the typical source of an alpha particle is radium-226. A typical source of beta particles is carbon-14, and then a typical source of gamma rays is technetium. So now I have an example of a carbon-14 nucleus, which is radioactive, as we discussed a second ago, right? And when it emits its beta particle, as you can see here, there's the emission of the beta particle, or its one high energy electron, right? It becomes a brand new element. It becomes a brand new element. And this element is nitrogen, normal, safe nitrogen. So we began with our radioactive nucleus, which had 8 neutrons and 6 protons, right? That's how you get the number of neutrons, 14 minus 6. And then now, after it has emitted its beta particle, you're left with, in this new atom, 7 protons, 7 neutrons, and 7 protons, and now you have a new nucleus of nitrogen plus 1 beta charge, or beta particle. So it's a pretty easy, simple example for a radioactive isotope becoming stable by emitting some kind of particle. And then the last slide is about measuring radioactivity and half-lives. So generally, we detect radioactivity using a Geiger counter. So this is a Geiger counter right here, right? That's how you detect radioactivity. And the units we use for detecting radioactivity or measuring the amount of radioactivity that's being emitted emitted is these units here. So if you're talking about activity itself, it's the Curie, named after Marie Curie, right? Um, if it's for the common unit, if you're talking about the Standard International or SI unit, we're talking about the becquerel, which I've never actually even heard of before. I've never used that before. But this is the conversion between the Curie and the becquerel. If you're talking about the amount of absorbed, amount of radiation absorbed, we call it the rad for the common unit. But if it's the Standard International unit, we call it the gray. For every 1 gray, there is 100 rads, right? And then I guess the most important unit we use is called the REM for biological damage. The SI unit is the sievert, and for every 1 sievert, there is 100 rem. Right, 100 rem. I just thought it was very interesting, this little chart I found here. If you remember the saying that only a cockroach can survive like a nuclear meltdown or something like that, or a nuclear apocalypse. I guess it's true because when you look at this chart here, life form, of course, you know what that is, but LD, right, 50, what does that mean? LD 50 stands for lethal dose 50. So what is the dose? What that means is, what is the dose that will kill 50% of the population, right? We're measuring this in sieverts, of course, right? But when you look at a dog, only 3 sieverts will kill 50% of the dog population, right? 50% of a dog population. For humans, only 5. So, we're not very resilient to radiation either, right? Rats, well, 8, so they're a little bit more resilient. But look at this, bacterium. Wow, 500. But I think the coolest or the most interesting is the insect. It takes 1,000 sieverts to actually kill an insect. Well, so they must have like some kind of radioactive blocking in their exoskeletons or something like that. And that's why they say that cockroaches can survive a nuclear blast or a nuclear apocalypse. It's very interesting stuff. So let's talk about half-lives now. The half-life of a radioactive isotope is the time that it takes for the radiation level or the activity to decay or decrease to 1/2 of its original value. So when you look at the example we have here, we have iodine-131, which is radioactive. And we start out with 20 milligrams of that. After 1 half-life, half of it is gone, so we're only left with 10 milligrams of iodine-131. The other 10 is now xenon. After 2 half-lives, we're left with 5 milligrams of iodine-131, and we're left with 15 milligrams of xenon. And after 3 half-lives, we're only left with 2.5 milligrams of iodine-131. So radioactive isotopes go through this kind of decay, and you can actually measure it. And so we have over here a chart of some very common radioactive isotopes and their half-lives and how long it takes. So carbon-14, for example, which we use a lot for carbon dating, right, has a half-life of about of 5,730 years, right? We just had iodine here as our examples. Here we go. Iodine-131. Its half-life is 8 days, right? So after the first 8 days, you go half, and you lose half of it, and it's at 10 milligrams. And then after 16 days, you lose another half, and it's at 5 milligrams, right? And then at 24 days, you're at 2.5 milligrams. So you can literally use the half-life to figure out how long ago a radioactive isotope has been sitting there. So let's do a quick example problem. Really simple. So I'm going to clear this so I can do an example problem. If you have the radioisotope of strontium-90, and its half-life is 38.1 years, right? 38.1 years, and you have a sample that contains 36 milligrams, how many milligrams will remain after 114.3 years? Well, it's actually super simple. We can do a little bit of dimensional analysis, and then we can do what I did a second ago with the iodine to figure out how much is left, right? So let's start out by saying what we started with here, which is 114. Let me clear that real quick, I messed up. So let's start out with 114 years, 0.3 years, right? And then for strontium 99, or sorry, strontium 90, one half-life is 38.1 years. So we got really lucky there because you can cancel out the years, and you're left with half-lives, right? And if you divide 114.3 divided by 38, you get an even 3 half-lives. Right? 3 half-lives. So now that we figured out that 114.3 years is 3 half-lives for strontium 90, let's figure out how much strontium is left. Strontium 90 is left after those 3 half-lives. So just to remind us, let's write down we need to remember that we're going for 3 half-lives. So after the first half-life, or we're starting out with 36 milligrams for the first half-life. After one half-life, it becomes 18 milligrams. And after the second half-life, it becomes 9 milligrams. And then after the third half-life, it becomes 4.5 milligrams. So what that means then is that you end up with, after 3 half-lives, or 114.3 years, 4.5 milligrams of strontium 90. So let's spend this last slide talking about some practical uses for radiation. Here in medicine, doctors can actually use iodine 131 to visualize the thyroid gland. Here we have a PET scan, or a PET scan. And PET stands for, or PET stands for positron emission tomography. So basically, positron emitters, or radioactive isotopes that emit positrons with having short half-lives, are combined with body substances like glucose, and doctors can use that to visualize the brain, as you can see in this PET scan here. You can also use it to track metabolism and blood flow too. Here we have a CT scan, and CT stands for computed tomography, and this is basically just using X-rays, taking a series of X-ray scans at successive layers of a bodily organ, and you can use that to visualize, for example, here the brain at its different layers. Other isotopes, radioactive isotopes, can be used to study the body too. For example, here we have technetium-99m, can be used to study the brain and the bone. We have strontium-85 that can be used to study the bone. We have iridium-192 for breast. We have phosphorus-32 for leukemia. Gallium-68 can be used to examine the pancreas. Gold-198 can be used to examine the liver. Cerium-141, the lanthanide, can be used to examine the GI tract. And both cesium and palladium here, cesium-131 and palladium-103, can be used to examine the prostate So those are the multiple uses for radiation in medicine. Another practical use of radiation is in energy production. So here we have an example. The first image is an example of nuclear fission. And then this is an example of nuclear fusion. They are different, but we'll talk about nuclear fission first. So in nuclear fission, we have a radioactive uranium-235. And scientists in 1935 did an experiment in which they bombarded uranium-235 with neutrons, right? It made the nucleus of the uranium-35 so unstable that it split. It split into krypton and barium, right? But in that process, energy was produced. A lot of energy was produced, right? And in addition to the energy, more neutrons were produced. And those neutrons shot out and bombarded more uranium-235, which split again into krypton and barium. And again, the neutrons from that split continued to hit more uranium-235 and split again. And so what we call that is a nuclear chain reaction. And a nuclear chain reaction is achieved when a critical mass of uranium-235 is bombarded with neutrons. And in this process, a lot of energy is made. A lot. So you can actually figure out how much energy is being made because of Einstein and his equation E equals mc squared. How, you might be wondering, can we use E equals mc squared to figure out how much energy we made? Well, we already know what c is, right? C is the speed of light. And the speed of light is approximately 300 million meters per second. Wow, that's a big number. Here, M stands for mass, right? And what is this mass? This mass is actually the missing mass after the uranium has split into krypton and barium. Once it's done that, split into krypton and barium, there's a mass, which you can determine by just taking the two masses of krypton and barium and subtracting it from the uranium, and you can plug it in there, into the missing mass. And that gives you E. So whatever number that is, which I'm not going to do the calculation now, but whatever that number is, multiply that by the squared of 300 million is a huge amount of energy. And I'm not even sure if that's the correct unit to be working with this here, but in either case, it's a lot of that's a lot of energy. So that's what nuclear fission is. Well, what's nuclear fusion? Well, nuclear fusion, two nuclei, smaller nuclei, combine to make a larger nuclei, right? So here we have two hydrogen isotopes that will combine with each other to make a helium isotope. and produce energy in a neutron. One neutron and some energy. So this is called nuclear fusion because instead of splitting, you're combining two smaller nuclei to make a larger nuclei. This usually happens at about 100 million degrees Celsius. Oops. That's supposed to be a degree sign. There we go, degrees Celsius. And most commonly occurs in the sun or stars. And this is much more efficient. There's a lot less waste here when you're doing this kind of nuclear fusion reaction. Right over here in nuclear fission, you're making waste products such as the krypton and the barium. Right, you're only really interested in the energy it produces, and then the neutrons that come out to make more as they hit and collide with more uranium-35 isotopes. So there's a lot of waste being made with nuclear fission. But in nuclear fusion, when you combine two nuclei to make a larger one, you're left with that larger nuclei and a larger amount of energy. So much more efficient that way. But when we talk about practically, though, like a nuclear reactor, let me clear that out. There we go. When we talk about nuclear reactor, these are actually fission nuclear reactors. Meaning they employ nuclear fission and not nuclear fusion, where, for example, uranium-235, right, where there's a lot of waste. So, just a quick explanation here. We have our nuclear reactor. This is where the reaction occurs with the uranium-235, and it's splitting and making a lot of energy, and splitting again, making a lot of energy and a lot of waste. Excuse me. And the reaction chamber, or the nuclear reactor, right, it has these pipes that have hot water or molten sodium inside, which go into a boiler that heat up water. And as they pass through the water and on the pipes, the water actually heats up and creates a lot of steam, right? The steam is piped into a steam turbine, and that steam turbine spins and creates electricity. And as it passes through, that's what it does, and then it ends up in a steam condenser. And when it cools, the steam turns into water, and that water is piped back into the steam generator. And then the hot molten sodium, or the hot water, cycles back through into the nuclear reactor and is heated up again and passed back through into the steam generator. Just to keep the steam condenser cool, so that it continues to condense the water vapor or the steam, so that it can be piped back into the steam generator. There is cool water continuously being pumped into the steam generator from a water source. And that's basically how a nuclear reactor works. And that ends our lecture for this time around.